Okay, let's introduce the rule for getting or showing or introducing a universal quantifier when you want one. As I mentioned before, the book and the proof checker do this differently. I'm going to start just by demoing how to do a proof using this rule, and I'm going to do it the proof checker way because it's simpler. And then I will do it again using the book way. Before we do that, let's start with a rule we definitely don't want. Okay, imagine that I gave you this argument. Let G be wears glasses and T be a name, Tanya. And I know it's from the middle of the alphabet, and we now said let's let those mean indefinite names, but I forgot about that when I wrote this proof, and because it's about me as an example and T stands for Tanya, that's what I picked for a name. So let T be an ordinary name, and G mean wears glasses. Premise 1 says Tanya wears glasses, and the conclusion says everyone wears glasses, assuming our domain is people. Clearly, that's a bad argument. Just because one person wears glasses, it doesn't follow that everyone does. That would be a hasty generalization, a fallacy. If we had a rule that said, well, if you have a thing, you can just stick a universal quantifier out front, like so, that would be a bad rule. It would allow us to move something true to something false. And the number one feature of all of our rules, the ones with the quantifiers and all the ones from part 1 of the course, is that they are truth preserving, that they embody validity or implication. If you apply them to true things, you're guaranteed to get true things. So we wouldn't want a rule like this. Let's start with a concrete example, and I'll just reason through it. I see that I have universally quantified statements, so I'm immediately thinking universal elimination or universal instantiation. And I want a universal quantifier, which we don't have a rule for yet, but let's just start with what we see we have and apply universal elimination. Okay, so I know. Also, let's stop and give an interpretation to our predicates just to make this more intuitive. Let's let C mean is a cat, M mean is a mammal, and W mean is warm-blooded, and let the domain be living things or something like that. Then premise 1 says all X are such that if X is a cat, then X is a mammal. All cats are mammals. 2 says all X, all things in the domain, are such that if that thing is a mammal, then that thing is warm-blooded. In other words, all mammals are warm-blooded. And the conclusion says each and everything in the domain is such that if it's a cat, then it's warm-blooded. All cats are warm-blooded. And intuitively, this is a valid argument, right? If all cats are mammals and all mammals are warm-blooded, then all cats have to be warm-blooded. Okay, so let's start with the rules that we immediately see. Let's let A be one of the objects in the domain, a name for one of the objects in the domain. And then let's do the same thing to premise 2. Okay, now what? Well, you might be thinking, these all have, in the premises, these all have the quantifiers out front, but the argument is if something's a cat, then it's a mammal. If it's a mammal, then it's warm-blooded. Thus, if it's a cat, it's warm-blooded. I know that I want to say something along the lines of, if something's a cat, then it's a warm-blooded. I want some kind of conditional. And if you've done enough proofs, this looks familiar. Like if CA, then MA, and MA, then WA, CA, then WA. And it looks an awful lot, at least like part of the conclusion. So if you're thinking, well, clearly we want a conditional. If CA, then WA. then we should be thinking of what rule allows us to get a conditional. And that's CP. Rule, proof method, whatever you want to call it. When you want a conditional, use a conditional proof. And so let's do that. Let's make an assumption. The assumption for a conditional proof will be the antecedent of the conditional statement we are trying to show or get. And previously, we have been justifying this step. We've been calling it assumption for conditional proof. The proof checker does not justify assumptions. Feel free to do it the proof checker way or the old way. Okay, we've got our assumption. Now let's do modus ponens. We've got a conditional on line 3, the antecedent on line 5, so we can infer the consequent, citing lines 3 and 5, and the new shorthand in the proof checker is conditional elimination. Feel free to also still write good old MP if you want, or if you're like the book, spell it out and write modus ponens. Doesn't matter. I'm going to do the shorter one, and I'm going to start doing it proof checker way. Okay, lines 4 and 6 is another application of modus ponens. Lines 4 and 6, modus ponens, or arrow elimination or horseshoe elimination. And now we got the consequent of the conditional we want on a line, so we are done with the subproof. The next line has to be a conditional whose antecedent is our assumption and whose consequent is the last line of the subproof. And we will justify that lines 5 through 7, CP. Okay, we're so close to the conclusion we're trying to get. And what the proof checker will allow you to do is just put the universal quantifier out front like so. Change all the A's to whatever variable you chose. Doesn't matter whether it's X, Y, or Z as long as you're consistent. And we'll cite just line 8 and universal introduction. And the question is, why can we do this? We just said previously we would not want to be able to do this. This is bad, but this one's okay. But this one's not okay. Why? They seem exactly the same. The difference will be that there are constraints on when you can do this step. And you can only do it when this letter that we've been using is not in any of the premises or in any open assumptions, should there be any. Okay, and it's not in any of the premises or in any open assumptions. If there had been something like, let's say there was another premise and it was like PA. If there had been the name A anywhere in a premise, it wouldn't have allowed us to do this. And by putting that kind of constraint on it, we prevent ourselves from making the hasty generalization. Okay, why exactly? Because if A has not shown up anywhere in the proof so far, it's not in any premise, it's not an open assumption, it's not been mentioned at all. When we first on line 3 choose A, we could have chosen any object from the domain, literally any name of any object from our domain, and we would have gotten the same result. And so the reason why we can take this last step down here and put a quantifier out front is because it didn't matter which object we chose. Choose any object, call it A, here's what follows. But it didn't matter that it was A. A was an arbitrary choice. A could have been any object. And that's why we're allowed to do this last step. Okay, now let's look at the book way of doing it. And I'm going to leave the proof checker way up for comparison. Okay, the book checker way, or the book way of doing it says, we're going to start by making an assumption. And this is kind of weird compared to some of the other ones. We're not going to give it a line. So we're not going to say line 3, make an assumption, because it's not something we're ever going to cite. we're going to just say, note for the rest of this subproof, when I write x prime, I take that to be an arbitrarily chosen object from the domain. Or maybe we could say something a little more deeply philosophical and possibly confusing and be like, it doesn't really represent an object from the domain. It represents an abstraction that has whatever properties we're talking about. The easier way to understand is let x prime be any object from the domain. It doesn't matter which one we're talking about. X could be anything. And from here on out, that's what I mean by x prime. Okay, then on line 3, I'm going to start my conditional proof. Okay, so just like I had a conditional proof before, I'm going to start a conditional proof for, basically, I'm trying to get this conditional here. Same conditional I was trying to get here. I'm going to make line 3 Cx prime. And this is basically my ACP. In the proof checker, you don't have to cite things, but I'll do it a little more like the book way. Assumption for conditional proof. Okay, then line 4, we are going to do our universal instantiation or universal elimination. Let's remove the quantifier from line 1. We'll make x prime. That's just line 1 AE, universal instantiation, universal elimination. And now an application of modus ponens to lines 3 and 4 gives us mx prime. Line 6, let's get the other universal statement instantiated. So let's choose if mx prime, then wx prime, and that is line 2, universal instantiation / universal elimination. Another application of modus ponens gets us to wx prime 5 and 6 mp, or arrow elimination. And we did it. We got from Cx prime to Wx prime. Wrap up that subproof. On the next line, you write down the conditional whose antecedent is the assumption of the conditional proof, and whose consequent is the last line of the conditional proof, and justify it with the numbers of the lines in that conditional proof, CP. And now we wrap this up and we say, inside this box here, this one I'm talking about right now, we have been just assuming any randomly chosen object or something more abstract than that. So let's now discharge that assumption and just say for all x, Cx, then Wx. And we are going to cite lines 3 through 8. Universal derivation is what the book calls this, or think of this as universal introduction. End of proof. Okay, so structurally it looks different. The book way of doing it is more complicated. In addition to drawing primes, it also says like, oh, also put a box around this, just so it's super clear that that is an arbitrary instance and that everything done within this subproof is using this arbitrarily chosen instance, which allows us to get to line 8. And since we could get to line 8 with an arbitrary instance, we could get to it with any object we choose from the domain. So all objects have the property that if they're cats, then they are warm-blooded. And that's essentially what is embodied here when you put some constraints on A. It can't be the premise in any of the premises, and it can't be in any open assumption. And you'll be guaranteed that A was a randomly chosen object. It could have been any object. And since we've proven something for something that could have been any object, we've proven it for all objects. Okay, let's do another one. And why don't you pause it and try it on your own and see how it goes? And maybe try doing it both ways, the book way and the proof checker way. But if you just want to do it the proof checker way, that'd be fine. Assuming you've already done that, let's get started together. So even though I know this is going to be a proof that allows us to show a universal quantifier, use that universal introduction rule, I'm still going to start my main problem solving way and look at what I want and what I got. What I want is a universally quantified statement. So maybe I will use universal introduction, and since that's the rule we are currently practicing, I probably will. I have universally quantified statements, so I'm thinking I'm going to use universal elimination. And then I'm also looking at what's inside the scope of these universally quantified statements, because those patterns will often look familiar. So look, we've got a conditional inside of one. We have the antecedent of that conditional inside one, and we've got the consequent inside of another one. So I'm seeing like something modus ponens looking pattern-wise here. So let's get started. I'm going to do it the proof checker way first because proof checker way is easier. Let's just start by doing things we can see, which is removing those universal quantifiers. Let's just pick A. Since A is not already used as a premise or anything else, when I pick A, I could be picking anything. Why A? Because it's the first letter of the alphabet, not for any special reason. A could be any object from our domain. And let's do the same for line 2. And now clearly I've set up something that looks like modus ponens, or as we'll now call it, arrow elimination. And I'm awfully close to here. At this point, I'm allowed to just introduce the universal quantifier. I replace the name with a variable. And I get to do this because when I picked A could have been any object from the domain. Therefore, it'll apply to all objects of the domain. Let's do it the book way. Okay, so we're going to start not with a numbered line, but we're going to start, and let me move this one out of the way just so it's a little like, okay, that's the one we just did. So now we're going to start here and we're going to say from here on out, and the way the book kind of draws it in, right, here's the main body of the proof. It'll look like this. We're going to start from here on out. I don't know how much space it'll take, but somewhere like this. Let's let x prime, and the convention here is to pick any variable and stick a prime after it, and then also box around it as if the prime doesn't do enough to specify what it is, just to make it clear, like, this is an arbitrarily chosen object from the domain. This is an arbitrary instance. So now we're going to reason about what must be true for this arbitrary instance. It could be anything, therefore we will conclude a claim about everything. Okay, line 3. Line 3 will be where you just start doing the proof, okay? From here on out, we're just using x prime, knowing that it's an arbitrary instance. But here's where you have to think about, what do you actually want to show? Last time, we started by starting a new subproof because we had reason to do a conditional proof, because we wanted a conditional. But here we don't want a conditional. What do we want? Sometimes maybe we don't know what we want. Maybe you're in that boat. Maybe you're like, I don't know what we want. I'm having a hard time working backwards. One thing you could do is just things that you see. What do you see? I see we can use universal elimination. We've got these universally quantified statements. Well, let's just start eliminating some. So I can do this, line 1, AE, and I can do the same thing for line 2. And now by modus ponens, I get this. And I got on my last line mx prime. Now I'm going to shorten up my proofs. So what I've shown so far is that under this assumption where I've randomly chosen some object from the domain, call it x prime, mx prime has to be true. And since it's true of some randomly chosen object, it's true of every object. Not we randomly picked one and we saw it was true, but we reasoned about what had to be true for a randomly chosen object. So it has to be true for everything. And if that difference didn't make sense to you, just let it pass. Okay. Done. So you can see that it really looks just like this one, with the minor difference that we highlight with a little inset subproof that x is an arbitrary instance, whereas with this one, we just assume we know what we're talking about, or we know that this is something that hasn't shown up in a premise or any kind of assumption, so it could have been anything.